What's up YouTube, and welcome back to the ASX Portfolio channel. So today we're going to be talking about the implementation of value at risk and conditional value at risk in Python, and specifically we're going to talk about historical method at the moment. So we're going to implement these two models, and we're going to use the historical method, the parametric method, and the Monte Carlo method over the next couple of series. So let's talk today about the historical method. I've borrowed some things from the Efficient Frontier episodes, and I will post the code on my website. So feel free to just use it direct or type it in yourself. But essentially the modules we're going to be using today: pandas, NumPy, datetime, and the pandas data reader, so we can read in the stock information from Yahoo Finance. So if you remember, we had the import data, get data, defining the stock list of stocks, the start date and the end date. We also had, so we're taking all the close prices, we're grabbing the returns as the percent change, which is what we're going to need for our analysis today. We've got the mean returns and the covariance matrix. I'm also borrowing the portfolio performance function that we built in the Efficient Frontier module, which we have the arguments weights of our portfolio allocation, mean returns matrix, covariance matrix, and I've actually added this parameter time because we don't want to look at the portfolio performance over an annualized period anymore. We want to define what the time step is and the time step that we're going to evaluate our value at risk over. So you can see that I've just simply multiplied the daily returns, mean weighted returns, by time, and of course the square root of time rule for volatility and standard deviation. Santos. So we have our stock list today: CBA, BHP, Telstra, NAB, Westpac, and Santos. So same as before, we define an end date, which we're just going to say now. We have a start date, which we want the historical period for. We just said 800 days ago, give us a lot of data. So then we compute in the returns, mean returns, and covariance matrix from get data with that following information. And then simply I'm dropping the NAs in the data set. And that's occurring because we're evaluating the percent change between days, and we're losing 1 day's worth of information, and that's degrees of freedom. So the first thing we want to do is we want to find out what our portfolio allocation is. Now, we're just going to set random weights for this portfolio. So weights is going to be equal to, we're going to use random distribution, which returns values from 0 to 1, as you can see in that function. And we need to define the length of this vector. And the length of this vector is going to be defined from the returns. More specifically, the returns.columns. So that's going to give us back the number of stocks that we have in this returns list. So if we add stocks to here, this will automatically update to the correct length. Now, if we're returning random values between 0 and 1, you can obviously guess that the allocation is not going to come out to 100% exactly, so we need to normalize by the sum of all these weights. So the next stage is just using weights, and we're going to use the division operator and equal to, so each element in this array is going to be divided by the NumPy sum of all the corresponding weights. So normalizing it so that all our weights add up to 1. So what I'm going to do here is print out the returns data frame. So Python returns, not returns, I've called this file VaR. And I want to do this to show you the structure of the actual pandas data frame. So we have dates down here on our index. On our columns, we have all our stocks. And of course, we have the corresponding percentage daily returns here in each column. So what we want to do is now use this weights vector and actually multiply each of these corresponding assets with that respective weight to then get the portfolio outcome for the day historically. So we're using the historical information to work out what our portfolio would have been if we had these given weights for it. So we're going to say returns. We're going to make a new column called portfolio. And we're going to make that equal to the returns. And we're going to do the dot product with weights. And as that's a numpy array, that should work out. Excellent. So let's print the returns now beneath that. Save, run. And we should have our portfolio on the right-hand side now with our daily returns. Excellent. So now we've used historical data to define a portfolio with those given weights. So now what we're going to do, we're going to use this portfolio theoretical distribution, and this is a historical distribution given those weights, and we're going to build our value at risk and our conditional value at risk functions. So let's define this as historical VaR. And we want to import the returns, and we want to import alpha, which is our confidence level. Now, we're going to set this at 5 if it's not defined. So the 5th percent confidence interval. So what do we want to do? Well, in this function, we want to read in a pandas data frame of returns or a pandas series of returns. What do we want to output? We just want to output one number, which is the percentile. We want to output the percentile of the distribution at that given alpha level. Confidence level. Excellent. So we have two scenarios here. One is it would kind of be useful to have the information for what the percentile was for each of these assets individually. And then also, of course, we're interested in just one, returning one value, which is the portfolio value. So we are going to check whether we're actually getting a series or a data frame involved. If we get the data frame with all the columns, then we want to specify what is the percentile for each column. But if it's just one series, we just want to return one value. So we're going to use the Python function isInstance to work out whether this returns data frame is a data frame or a single series. So let's use if isInstance. Let's start off with a case that it is going to be a pandas series. So we're going to have the object that we're interested in investigating, which is the returns data frame. And what we want to say is it of type pandas data frame series. Now, if it's a series, what we want to do is we want to return the percentile. So we want to return numpy percentile of returns, and we want to return the percentile to alpha. So it's going to be automatically 5th percentile. So what we want to do here is check if the returns is an actual pandas data frame. If it is, we want to use a special function within pandas called Aggregate, or ag for short. So using this function, I'll just copy what the definition of it is here. So essentially what we can do is we can pass a user-defined function of a series for evaluation, and what that's going to do is evaluate the function for every column of that data frame. So it's going to pass each series individually. So let's go else if isInstance returns PD data frame, and what we want to do is return returns dot aggregate, and what we want to do is actually pass the function historical VaR, okay? And the actual conditions that we're going to use for that is alpha. Excellent. So for each one of these column headings, it's going to return the historical VaR. So essentially, each time it hits this, if it is a pandas data frame, we're just going to return the percentile value. So we also want to error check this function, and essentially, if else, we want to raise a type error. Type error, what do we actually want to say? We want to say, well, we expected returns to be data frame or series. Excellent, and that's just going to make the user aware whether we're trying to import data that is nonsensical for this function. So that's historical VaR. Let's just quickly print and test that function, historical VaR, and let's first test the pandas data frame with an alpha value of 5, and let's see what we return from that function. Excellent. So as you can see there, it's correctly identified that we want to aggregate via the historical VaR function, and then returned the percentile at the fifth, alpha equals 5, so the 5th percentile of each one of those individual distributions, including for the portfolio, but this is the one we're most interested in. So how we're going to access that is just by simply referring to the series with a column portfolio. So that's just going to import one series, and we're going to return the percentile as a value. So that's our historical VaR done. Let's actually start building our conditional value at risk. So we're going to then define a function in the same way. Historical conditional value at risk. And we're going to get the returns and the confidence level alpha. So we'll copy, so we're going to read in pandas data frame of returns, or a pandas series of returns, and the thing we're going to output is, of course, the conditional value at risk for that series or pandas data frame. So output the conditional value at risk for data frame or series. I might just... Excellent. So we're going to use the same structure here. We're going to test whether it was a series and whether it was a return. So we're just going to copy the function from there. Excellent. So isInstance, what are we going to do if we just have a series? So what we need to do with this function is actually check for all values in our distribution, is that above or below VaR? So we're only interested in the numbers below VaR, and we want to take the expectation of that. So below VaR, we'll call this. And the way we're going to define this is we're going to take the pandas data frame returns, and we're going to make this subset of the data below or equal to the historical value at risk with returns and alpha. Alpha equals alpha. So what's this going to do? It's going to feed in the returns. It's going to select all of the returns within, it's going to select all the returns within this range below the value at risk that we're calculating. So we want that 5th percentile. So what we can do now is take our returns with that condition now below VaR. So I only want to select the returns that are below VaR, and I want to just take the mean. I want to find out the expectation of that loss. What are we going to do if it is a pandas data frame? Well, actually, we're going to return the aggregate of all the historical CVaRs. So we're just going to, for each header column, again, return this value. So let's test that out. So historical VaR, we've got returns, alpha. Let's send the whole pandas data frame down there first. Bang, and that looks about right because that's a lot less than our actual functions were for value at risk. So that's a good sense check, making sure that that expectation is less than the VaR limit that we were calculating. Of course, this portfolio weights are randomized, so it could be different. But now let's go returns portfolio. And we should just be returning that value there. Excellent. So now let's be specific. We only care about our portfolio. So let's print out all this information. So we want to call this CVaR. We want to call this VaR. And we're going to take the historical VaR. Those functions look pretty similar actually. Maybe we should change that definition. Oh well, should do for now. The other useful things when you're looking at risk statistics is, this is a measure that looks at what is the value almost from the expectation to the percentile. And when you're looking at this kind of metric of variance away, you want to know what the expectation is over a given period of time as well, not just this loss value. So that's why I've included this portfolio performance function. So we can find out the portfolio performance, and we're returning portfolio returns and standard deviation. So P return and portfolio standard deviation is equal to weights, mean returns, covariance, and time. So what time horizon are we interested in? Let's define that here. So the time horizon, let's say for at the moment, we're interested in 1 day. So 1 day, we're going to multiply the VaR by the square root of time rule, and the same with the conditional value at risk. Square root of time rule, it's your best friend. In the portfolio performance, it's going in as time, and it's square root for standard deviation, and it's just scalar for returns. So let's print this information. So we're going to assume that we have a portfolio of $100,000. So initial investment equals $100,000. So given that we have the returns, the value at risk, and the conditional value at risk as a daily percentage change at the moment, we're going to just simply multiply by the initial investment. So let's print out expected return or portfolio return is going to be round the initial investment times by the P return. And let's just go to 2 decimal places. Our value at risk at the 95th percentile or 95th confidence interval is going to be our initial investment times by VaR and our conditional value at risk it's not very neat. Conditional value at risk at the 95th percentile is going to be equal to the initial investment times CVaR. Let's print that out and see if that's neat enough for us. Excellent. So actually we've returned the negative values. So obviously we're interested in finding out what the value at risk, what our downside is, but by that definition, we actually want that to be a positive value. So all we need to do is define VaR as the negative historical VaR there and the conditional value at risk as the negative historical. So there we have our loss measures. Over a 1 day time horizon, we expect to make $6, so pretty small, obviously. But at the 95th confidence interval, we're happy that we're not going to lose any more than $2,340. In the days, historically, with this portfolio, in the 5th percentile, the lowest 5th percentile, what is the expected loss that we have, or the expected shortfall is another name for it. And in those circumstances, we would expect to lose $4,325, $26. So that's really important. It's really important to have the conditional value at risk, because when the distribution to the downside is extremely skewed, as it would be represented in the historical data, it's really important to understand that given that level of risk, what is the worst case scenario and the expectation of that worst case scenario. So obviously we've defined this function here by time. So, I can change this to 10 days and print out the 10-day expected portfolio return and then the value at risk and the conditional value at risk in the 95th percentile using the historical data. But what we're going to do in the next couple of episodes is actually implement the parametric method and the Monte Carlo method. So stay tuned for that. Thank you very much for listening, and as always, please subscribe and hit the like button. Thank you.